When two atoms come together to form a covalent bond, there's an ideal distance, which we call the bond length. The energy change at that distance is what we call the bond energy, and this reflects the strength of the bonds. In many cases, we can compare bond lengths and bond strengths in different molecules. In order to rank bond lengths and strengths, we need to know that they track bond orders. We can think about a continuum of bonds, from a single bond to a double bond to a triple bond. When thinking about length, single bonds tend to be long, whereas triple bonds tend to be short. Double bonds would be intermediate. With bond strength, single bonds are weaker, triple bonds are stronger, while double bonds are again intermediate. The bond energy is related to the bond strength. Weak bonds have small bond energies, while strong bonds have large bond energies. It is worth noting that when resonance is present and leads to fractional bond orders, we can place those bonds on the continuum as well, intermediate to single and double, or to double and triple. The first question asks us to rank the CO bond in these three chemical species in bond strength, bond length, and bond energy. In order to do so, we need to determine the bond order in the three structures. In structure A, the CO bond is a double bond, so the bond order is 2. In structure B, each CO bond is a single bond, so the CO bond order is 1. There are no resonance structures in A or B, but in C, we should recognize that there is another resonance structure with the double bond to the oxygen on the right. The CO bond order in this structure is 1.5. Once we have the bond orders, we know that structure B with a bond order of 1 would be the weakest, while structure A with a bond order of 2 would be the strongest. Structure C would be intermediate. For bond length, the ordering is the other way, with the double bond in A being the shortest and the single bond in B being the longest. Bond energy takes on the same order as bond strength. The weakest bond in B has the smallest bond energy. The picture in the second problem shows the energy curve for the formation of a carbon-carbon double bond with a minimum at point A. If we want to know where the minimum is for a single bond, we need to understand what the plot is showing and how a single bond is different from a double bond. First, a single bond should be longer. The x-axis, labeled r, gives the distance between the nuclei. Since the single bond should be longer, its minimum should be at a larger value. So points D and E would be possibilities, and we can eliminate B and C. The carbon-carbon single bond should be weaker than the double bond. It would have a smaller bond energy. The energy in the plot is an interaction energy. It represents how much different the energy of the system is when the atoms are bonded versus when they are separate. On the plot, the bond energy is the difference between the bottom of the curve and zero energy, shown by the dashed line. If the single bond has a smaller bond energy, its curve should be shallower and its minimum would not be as low. Point E would represent the minimum of the single bond curve. These four structures are not shown with any lone pairs or formal charges, but we assume octets of electrons around each atom. We want to know which has the longest NO bond. We know bond length relates to bond order, so we should find the NO bond order in each structure. In the first structure, there are 3 possible resonance structures, all equivalent, in which the double bond can move. With 2 single bonds and a double bond, the average bond order is 1.33. In the second structure, the triple bond would have a bond order of 3. In the third, the NO bond order is about 2. You might ask why this one isn't the same as the first one. Why can't the double bond move around? Well, it can, but if you form a double bond to a chlorine atom, it will take on a positive formal charge while the oxygen will take on a negative formal charge. Recalling our rule that zero formal charges are better than non-zero formal charges, this is a poor resonance structure and will not contribute significantly to the properties of the chemical species. The fourth example has two resonance structures with a single and a double bond, which gives it an average bond order of 1.5. The longest bond should correspond to the smallest bond order, so the first structure should have the longest NO bond.